All right, welcome to the last video of this course. We are going to be wrapping up this Intro to Linear Algebra class by covering section 6.6, an application to linear models. So as I mentioned at the end of the last video, when we talked about least square problems, we started with that section to lead into this application section, because if there's one type of approximation that majority of STEM majors use in their discipline, it is regression. Now, this book titles the section linear models, and that's fine. We're going to do more than just linear models. We're going to do 3 different kinds of models today, but the idea is still behind. We're trying to approximate the best answer possible. So what I want to do for the first 5 or 10 minutes of this video is I want to talk about the idea of what they call a least squares line, which other disciplines, like I said, call regression. So experimental data often produces points that when graphed seem to lie close to a line. Let's say, and here's my line we're going to use today. Let's say, assume the equation is y equals beta naught plus beta 1x. We want to determine the parameters beta naught and beta 1 that make the line as close to as many points as possible. So over here on the right, using this little graph here, the idea that we're about to get into is, let's assume you plot a bunch of data points that you have found. So let's assume there's one here, one here, one here, one here, and one here. You're not going to find a single line that crosses all those points exactly. It's just impossible to do. So instead, what this idea of least squares lines is going to do is that we are going to find, and I'm going to try to highlight the best I can, we are going to find a line that if you were to add up, let me change colors here. If you were to add up all these errors, it would be the minimum addition of errors that you can find. So you're trying to find a line that gets as close as possible to all your data points, even though it may not cross them all exactly. So here's how we're going to do that. Let's assume that you are given whatever number of data points the problem has. So each data point is denoted as x1, y1, x2, y2, etc. What we're going to try to do, all right, is we're going to try to write the best line possible. We want to minimize the distance between the observed and the predicted values. So in our data points, all of the y's are the observed y values. Those are the actual values you got by collecting your data. What I'm trying to do is predict it by using a linear equation for every single one. If we can minimize this distance, that's the best thing possible. Now, in the last section, we used the matrix equation AX equals B, and when we wanted to minimize our error to find the best solution possible, we were trying to find what is X hat. Well, it's going to be similar in this section, but we're going to use some different variables instead. So here's how we're going to start it. Let's rewrite the matrix equation in a slightly different way. Let's call, instead of calling it matrix A, let's call it matrix X. Instead of calling it vector X, we're going to call it vector beta, because that's going to be our unknown here. And then instead of B, we're going to call it the observed value or observed vector. We'll call it the Y vector. In this matrix equation, here is how those 3 things are denoted. Your matrix X is encompassed of columns that make up the coefficients of your variables. Let me repeat that again. The columns of X come from the coefficients of your variables. So remember, back up at the very top, we're trying to use the formula y equals beta naught plus beta 1x to approximate this line. Now you'll notice your first unknown is going to be beta naught. Attached to this beta naught is an unknown 1, because there is no variable attached to it. So since there's no variables attached to beta naught, we assume all the elements of the first column are the number 1. Versus your variable beta 1 that you're going to find has a, coefficient beta 1 that you're going to find has a variable of x attached to it. So therefore, the second column that's going to be used to help you find beta 1 needs to encompass all the x values of your data points. So we would just list all of the n number of data points you have, well, you only need the x coordinates for right now. The next thing in this equation is the vector beta. This is your unknown. This is what we're going to be solving for in just a second, or at least the best we can. And finally, your vector y, or your observed vector, that's just the y elements of your data points listed as a column vector. Please just make sure that when you list your vector y values out, that you are matching them up with the order that you listed the x values in. Now, our goal is going to be to solve for beta in this problem. Unfortunately, as you know, we're not going to find a beta that's exact. So instead, we've got to use our formula idea that we learned in the last video to find the best approximation. So if you remember what we did, so x beta equals y. If you multiply both sides of the equation on the left-hand side by x transpose to get the following, and x transpose x, remember this is called the normal equation, x transpose x would become a square matrix, and thus you could multiply it by its inverse to move it to the other side. So instead of finding beta, what you're going to do is you're going to have to find beta hat, which will always come out to be x transpose x inverse times x transpose y. This is the big formula in today's lecture. That looks very similar to the formula we used for x hat in the last video, but we're using x instead of a, and we're using y instead of b. So it's the same formula. You're just going to be tasked with writing your own matrices and vectors before you can actually do this problem. All right. So let's do a kind of a simple example here where I'm going to give you, let's see, in this case, 4 data points, and we want to write the best line that approximates this. So what is the equation y equals beta naught plus beta 1x of the least squares line that best fits the given data points? So in this equation, you need 2 things. You have to make up your own matrix x, and then we will have to make up our column vector y. So now remember, matrix x is denoted by the coefficients, or the variables, I should say, of your coefficients. So attached to your beta naught, there is nothing. So it's understood to be a 1. Since there are 4 data points, I have to encompass this by putting 4 1s down the first column, because you still have to match the number of data points. Versus attached to your coefficient beta 1 is an x. So for your second column, you have to list the x values of every data point. So that's -1, 0, 1, and 2. A little bit easier to do is you need your column vector y. So your column vector y is just the vector of your y values in order. So 0, 1, 2, and 4. All right, the formula we just went over says that beta hat will be x transpose x inverse times x transpose y. So let's figure that out. First of all, x transpose x. So that will be 1, 1, 1, 1, -1, 0, 1, 2 times the matrix x. So a 2 by 4 multiplied by a 4 by 2 matrix is going to be a 2 by 2. So doing my row column rule, we should get answers. Let's see, first row times the columns would be 4, and then -1 and 1 cancel, so that should be 2. Second row times the first column should also end up being 2. And then second row times the second column is going to be 1 plus 1 plus 4, which is 6. Now, I'm actually going to lay out my formula for beta hat all at the same time here. And here's what I mean by that. For beta hat, this is going to equal, I need to find the inverse of this x transpose x matrix I just found. So we have an algorithm for a 2 by 2 inverse. It would be 1 over the determinant of x transpose x. Well, my determinant here is going to be 24 minus 4 which is 20. And then for the matrix, you're going to interchange the main diagonal and negate the non-main diagonal. Then you're going to multiply this by X transpose. And then you're going to multiply this by Y. So this is a little bit different than how I did it in the last video, but I'm just trying to give you options of how to do this. Now, you can multiply these in whatever order you want to. My only suggestion for y'all is let's leave the 1 over 20 until the very end, because I don't want to deal with ugly fractions or decimals unless I have to. So this would be 1 over 20. Let's just leave the 6, -2, -2, 4 for now. I'm going to multiply the 2 by 4 matrix times the 4 by 1 to generate a 2 by 1. So the row of all ones times the single column should give you 3 plus 4 is 7. And then my second row times the column should be, that's 0, 0, 2, and 8 is 10. So then this would be 1 over 20. And I'm going to do a 2 by 2 times a 2 by 1, which will be another 2 by 1. First row times the column would be 42 minus, what is that? 42 minus 20, which is 22. And then second row times the column would be -14 plus 40, which is 26. So I'm going to multiply the 1 over 20 through, and you should get 22 over 20, 26 over 20, which those both reduce into, this one is be 11/10, and this one would be 13/10. So depending on what the homework asks you to do, if it's asking you for a fraction answer, this would be your solution. So I'm going to box this one in for right now. If they want the decimal, obviously get your calculator out and type that in. This would be 1.1, and that would be 1.3. Now, for your homework, after you find the numbers, they're going to want you to put it into the equation form. So you're going to go back to your original equation. And remember, the first number you found was beta naught, because that's how you labeled the first column. And your second number is your beta 1, which is how you labeled the second column. So if I was writing this as an exact answer, this would be y equals 11/10, because that's my beta naught, plus my beta 1, which is 13/10 times x. If the homework asks you for decimals, y would equal 1.1 plus 1.3x. And so this is the linear equation that if you were to graph these 4 data points and also graph this line, it would be the closest to all 4 of those points. And that is the idea of least squares lines, also known as regression lines. Now, a lot of people stick to just doing regression lines, and that's perfectly fine if that's how your discipline goes. But to end this class, I want to show you that you can actually do this for any number of equations. Now, there is more than what I'm going to list here. I just wanted to list a few to get your mind thinking this way. So when data points, let's say x1, y1 through xn, yn, when they fall on a scatter plot that do not lie close to any line, it may be more appropriate to postulate some other functional relationship between x and y. Once again, while these are not all of them, here's a couple examples. If your points fall more into a parabola form, maybe it's better for you to use a quadratic equation instead. So we would do beta naught plus beta 1x, and I would add a beta 2x squared term. Maybe you need to do cubic. Y equals beta naught plus beta 1x. You've got the beta 2x cubed, and then you have to also add a beta 3x cubed. And this, like I said, this can keep going and going for any degree polynomial you can think of. But keep in mind, the more variables you have to solve for, or coefficients, the more work you're going to have to do. So we're going to do one of those in just a second. And then to end this section, I am going to show you an example of a trigonometric regression. So one of the more popular ones involves just cosine and sine, because those are both periodic functions or waves that let people use. So the formula that I'll use a little bit later is that y equals beta naught times cosine plus beta 1 times sine. Once again, these are just three that I've made up for you. You can combine any combination you want to. You can make these as ugly as you want to. Just remember, the uglier you make them, the harder it is to compute the matrix algebra. So let's do an example of one of the polynomial curves I showed you, and we're going to do a parabola equation. So a certain experiment produces these 5 data points. I want you to find a model that produces a least squares fit using the quadratic regression formula. So we've got to find a beta naught, a beta 1, and a beta 2 that if we plug in will be the best fit to these 5 points. So we got to find a few things here. Number one, we got to find our matrix X. Since there are 3 unknowns, we're going to need 3 columns to generate all of this. Going with the variable of each. There's no variable attached to beta naught, so that's understood to be 1. There are 5 data points, so I'm going to put 5 ones down the first column. The variable of beta 1 is x, so I'm going to list the 5 x values down the middle column. That's -2, -1, 0, 1, 2. And then beta 2 has a variable of x squared, so you're going to square your 5 x values from the data points to get that column. That would be 4, 1, 0, 1, 4. And then right next to it, we can say that our observed value y vector is going to be the y values 1, 0, 1, 4, 9. All right, so we got to find some information here. Going the same path as the last problem. Next thing I want to do is I want to find x transpose x. So I need to write out x transpose 1, 2, 3, 4, 5, -2, -1, 0, 2, 4, 1, 0, 1, 4 times the original matrix. Okay. This is going to be a 3 by 5 times a 5 by 3, so at least the matrix gets a little smaller. You should end up with a 3 by 3 matrix here. So we got some number crunching to go through. I'm going to go through this really quickly, but like I said, if you need to pause the video and try it yourself, you can do that. So I'm going to do the first row times each column. That should give you a 5. That should give you a 0. And that should give you a 4, 8, a 10. Second row times each column, that's going to end up giving you a 0. That's going to give you 4, 8, 10. And then that's going to give you -8, -1, 1, 8. That's 0. And then finally, last row times every column, that's going to end up being 10. And that's going to end up being -8, -1, 1, 8, 0. And then 16, 16, 32 plus 2, 34. So that's x transpose x. Now, one of the other downfalls of having 3 variables here in this case is that you did get a 3 by 3 matrix. And remember, we have to find the inverse of this matrix. There's no fancy algorithm or formula to do that. So we're going to have to do row reduction to find this. So coming down to the next line, I now need to spend a little bit of time by finding the inverse of x transpose x. So going back all the way back to chapter 2 when we first did this, you would have 5, 0, 10, 0, 10, 0, 10, 0, 34, and then you're going to attach the identity matrix to that. So putting this into reduced echelon form, I'm going to begin by taking row 3 and subtracting 2 row 1s. 0, 10, 1, 0, 0, 0, 10, 0, 0, 1, 0. And so we will get 0, 0, 34 minus 20 is 14. That's going to be -2, 0, and 1. All right, let's see. Not the best numbers possible, but we'll make do. I'm going to go ahead and scale things. It really doesn't matter when we do this, but let's go ahead and just do it now. So I'm going to take three things here. I'm going to take a fifth of row 1. I'm going to take a 10th of row 2, and I'm going to take a 14th of row 3. Once again, just kind of the way I want to do it here, and we're going to get fractions, but we'll deal with them. So you should get 1, 0, 2, 1/5, 0, 0. Then you're going to get 0, 1, 0, 0, 1/10, 0. And then by a 14th, that would be 0, 0, 1, -1/7, 0, 1/14. And so now I need to get rid of that 2 on the top of column 3. So I'm going to take row 1 and subtract 2 row 3s. And that will give me 1, 0, 0. And so we've got 1/5, and that's going to end up being plus 2/7. I got to do a little scratch work here. So 1/5 plus 2/7. Let's see, that's going to end up being 35 on the bottom. So that is 7 over 35 plus 10 over 35. So that would be 17/35. And then you've got 0 minus 0, and then 0 minus 2/14 would be -1/7. And thankfully, nothing else changes. All right, we got the original matrix into the identity matrix, and I'm not going to write this all out again, but for future reference, this is now our X transpose X inverse. I'm going to go ahead and add a new slide because I know I'm going to need it. So now that we have X transpose X, I can begin the process of starting to solve for beta hat. So beta hat is going to equal the inverse we just found. So 17 over 35, 0, -1/7, 0, 1/10, 0, -1/7, 0, 1/4. Oh, sorry, 1/14. Bad handwriting there. That would have been bad down the line. That is 1/14. Yep. All right, so it's X transpose X inverse multiplied by X transpose, which we got from earlier, which is 1, 1, 1, 1, 1, -2, -1, 0, 1, 2, 4, 1, 0, 1, 4, multiplied by my vector Y, which is 1, 0, 1, 4, 9. All right. I'm going to try to avoid those fractions till I have to. So I'm going to multiply the last two matrices together. So we're going to have the 17 over 35, 0, -1/7, 0, 1/10, 0, -1/7, 0, 1/14. And then a 3 by 5 times a 5 by 1 should give us a 3 by 1 column vector. So let's take each row and multiply it by the column. So that would be 1 plus 1 is 2, 2 plus 4 is 6, 6 plus 9 is 15. So there's that. Second row times the column, that's -2, 0, and 0. -2 plus 4 is 2, and then 2 plus 18 would be 20. Last row times the column, that would be 4. Those both go to 0. 4 and 4 is 8. 8 and 36 is going to be 44. All right, 3 by 3 matrix times a 3 by 1 is going to be our final 3 by 1 matrix. This is going to be our final solution. Just be careful, use your calculator if you need to. So we got, let's see, first row times the column. And I'm going to have to use my calculator here, so I go ahead and apologize now. what is that? 17 times 15, and I'll do the scratch work down here. That is 255 over 35 minus 44 over 7, which will be 255 over 35 minus, got to reduce that one, that's 220 over 35, which becomes 35 over 35. So that's the best news you could have heard. The first answer is 1. The second row times the column's a lot easier because you're just doing 1/10 times 20, which is 2. And then finally, multiplying the last row times the column, you should get negative 15 over 7 plus 44 over 14, which is negative 15 over 7 plus 22 over 7. That's really nice. 7 divided by 7 is 1. And so you have found your 3 beta values that find the best approximation possible. You may not have thought it was ever going to get there, but going through the process and finding each thing, we have just found our beta naught, our beta 1, and our beta 2. So thus, the best quadratic equation that fits the mold of those points I gave you earlier would be y equals 1 plus 2x plus x squared. That is your quadratic regression formula. And so a lot of number crunching. So we don't do a whole lot of problems in these sections because they take a while to compute by hand. All right. And last but not least, to wrap up this last video here is I want to do a trig regression with you. So we're not going to do near as many variables, so maybe it won't take as long, but you got to be comfortable using your calculator to find some of these values. All right. Or you got to know your trig values from calculus classes and honestly trig class. So we have a certain experiment that produces 3 data points, 0, 1, pi over 4, 2, and pi 0. Describe the model that produces a least squares fit of these points by using the regression formula y equals beta naught cosine x plus beta 1 sine of x. And just for the final answer, we're going to round our final things to 5 decimal places because these are not going to be pretty. So third time's a charm. First thing, set up your matrices. So matrix X, there's 2 unknowns. So we are going to need 2 columns here. All right. For beta 1, sorry, for beta naught, you have a cosine function attached to it. So you have to take the cosine of the 3 x values that I've given you, and that will make up your first column. So cosine of 0 is 1. Cosine of pi over 4 is root 2 over 2, and cosine of pi is negative 1. All right. For your second column, your beta 1, you've got sine, so you have to take the sine of the same 3 x values and make up your second column. So sine of 0 is 0, sine of pi over 4 is root 2 over 2, and sine of pi is also 0. All right, so then we have our vector y, which is just the y values. That's going to be 1, 2, 0. And now we start computing the necessary information to find beta hat, beginning with x transpose x. So x transpose, if I transpose the rows and columns, multiplied by the matrix X that we created, two by 3 times 3 by 2, that's going to end up being a 2 by 2 matrix. So first row times the first column. Let's see. That's going to be 1 and 1 is 2. And let's see, 2 plus, that's going to be 2/4 or a half. So 2 plus a half is going to be 5 halves. And then first row times the second column would just be 2/4, which is a half. Second row times both columns, you should get a half again by our trends we've been seeing. And then last row times last column is also going to be a half. All right. So moving down to find my beta hat, we'll do this in green. Beta hat is going to equal, since X transpose X is a 2 by 2 matrix, its inverse is a little bit easier to find. So it's going to be 1 divided by the determinant of this matrix, which will end up being 5/4 minus a fourth. You interchange the main diagonal and you negate the non-main diagonal. All right, so that's going to be X transpose X inverse. Then you got to multiply this by X transpose. And then you multiply this by your vector Y. All right, so I'm going to kind of do this in the same order I've done every single one so far. This is going to end up equaling. Now, the nice thing about 5/4 minus a fourth is that's just 1, and 1 divided by 1 is just 1. So technically, this whole thing kind of just goes away because it's just going to be the number 1. I'm going to leave the fraction, the matrix with the fractions alone for right now. And if I multiply the 2 by 3 times the 3 by 1, I should get a 2 by 1 vector. So first row times the column, that's going to end up being 1 plus root 2. Once again, don't do your decimals yet. We will get to the decimal part in a minute. Leave it as exact answers as long as we can. All right. And then second row times the column, that's just going to end up being root 2. So now here's where I would let your calculator take over as you do this. So we're going to take this 2 by 2 times this 2 by 1 to generate another 2 by 1 matrix. And so we're going to take these elements times this column. All right. So let me get my calculator out so I can do this the best I can. So I'm going to take 1 plus the square root of 2. All right. And I'm going to divide that by 2 to get that number. And then I'm going to subtract from this root 2 over 2. All right, and you should get an answer. That's actually really nice. That just comes out to be 0.5. So then double checking the other one, we're going to take this second row times the same column. So let's do this again. We're going to take 1, we're going to take 1 plus the square root of 2 and get that number. And that's going to be divided by 2 with a negative in front because it's a negative 1/2. And then you're going to add to this, I'm going to open a parentheses and do 5 times the square root of 2 divided by 2, close parentheses, equals, and I did not get a very nice number this time. I got 2.3, it wants 5 decimals, 2843. All right. So based on this, all right, if I were to write out, remember, this is going to be my beta naught. This is going to be my beta 1. So if I were to write this in my equation form, y is equal to 0.5 times cosine of x. And then we're going to add to that 2.32843 times the sine of x as my regression or trig regression of these 3 data points. Now, you're going to see a pause here in the video. The fact that I got a really nice number on the first one and a really ugly number on the second one, I just want to make sure that I actually type that in my calculator correct. I'm using my iPhone calculator, so that may not have been the best. So you're going to see a random pause for a second, and I'll be right back. All right, sorry about that. I was correct. So I'm glad my iPhone calculator did not crap out on me, so that's always good. But like I said, always just double check, especially when you get these weird numbers. Sometimes it's kind of misleading, but very good. This is our regression answer. And so, sorry for the random pause at the end, but that officially ends the video for 6.6 and ends the last video that we are going to do for this class at Mississippi State. So we have covered everything from section 1.1 through 6.6. The only chapter we did not do in this class was chapter 4, and then a couple of other random sections that I skipped over that really weren't necessary for the curriculum that we do. I hope you've enjoyed the series of videos and enjoyed the class overall. Look out my YouTube channel. I also have videos for my Calculus 2 class, and I also have videos for my Intro to Business Cal class that I teach at Mississippi State. Y'all have a great day.